to add that negative sign because it's exothermic. Now let me show you how to use these enthalpy changes. For 4 moles, it's per 4 moles of ammonia. So how do we write these? There are 2 ways. First of all, the first way would be to write the heat as a reactant or product. And so I've got an exothermic reaction here, and remember, exo means heat goes out, so heat is a product in the reaction. And so I've got my energy term here. So when we make sodium chloride and water, we also make 54 kilojoules of heat. Okay, now in endothermic reaction, remember, this one is where heat is absorbed. And so look where my energy term is. It is as a reactant. So to take that 4 moles of NO and 6 moles of water, we're going to need to add those kilojoules to get this reaction to go. So that's the first way, as a reactant or a product. And then you determine which side it goes on based on endothermic or exothermic. Now the second way is you write the reaction, and then over to the side you're going to write delta H equals and then blank kilojoules, okay? And it could be positive or negative. So you're going to write the reaction, and then beside it tell what the enthalpy change is. Now the sign is going to be very important, and so you're going to have to add the sign here. So let's look at an exothermic reaction. Remember, heat is produced. So here's my reaction, and look how I'm going to write my enthalpy change. I'm going to add that negative sign because it's exothermic and heat is produced. Okay, and so this is for exothermic. Then my endothermic reaction, of course, heat is absorbed, and so I'm going to leave that as put that as a positive sign. And so you're telling the person who's looking at this reaction whether it's endothermic or exothermic. Now let me show you how to use these enthalpy changes. This is important. That's why it's in yellow, okay? So the delta H that is written for a reaction is for the number of moles exactly as written. So here's a little fake reaction, and this is endothermic, right? Because it's positive. So I have to put in 100 kilojoules for how much? For exactly 2 moles of A and 1 mole of B. I hope that makes sense. So it's exactly as written. Well, what if I were going to double this and use 4 moles of A and 2 moles of B? Then I would need to double my heat that I'm putting in, okay? And then I'm going to show you how to use the delta H as a ratio. So let's work a little problem here. So the given in this problem is moles of NO, and so I'm going to start with that. I have 1.5 moles of NO, and then I'm going to use my enthalpy change as a ratio. Watch this. I need to put in 1170 kilojoules per the number of moles of NO in my reaction. Well, 4 moles of NO take, so let me write this, moles of NO. 4 moles of NO need 1170 kilojoules. So when we multiply by this ratio, we get exactly the number of kilojoules that we need for 1.5 moles. Okay, because the reaction is written for 4 moles. So this is how you use enthalpy change as a ratio. Let's do one more. This time we're starting with grams of ammonia. So that's my given. I have 5 grams of ammonia. Now, you guessed it, I've got to go to moles there. So 1 mole of ammonia is 1704 grams of ammonia. Okay, now I've converted grams to moles. Why? Because this little enthalpy change, that enthalpy value is for the number of moles in the reaction. Well, this time I'm talking about ammonia. And so what I'm going to do of ammonia. Okay, and then we'll just cancel units, grams, grams, moles, moles, and we're left with kilojoules. Okay, and so we just do the math, and that's 5 divided by 17 times 1170 divided by 4, and we get 86 kilojoules. That's exactly how much energy we will need to absorb to react 5 grams of ammonia.